So let's look at how free energy and equilibrium constants are related. So we're going to relate the delta G for standard formation to the equilibrium constant. So the thermodynamic equilibrium constant K, this is the equilibrium constant in which the concentration of gases are expressed in partial pressures in atmospheres, whereas the concentration of solutes in liquid solutions are expressed in molarities. So we're going to do a little review of K. So the question is asking you to write the thermodynamic equilibrium constant K for the following. Ammonia gas plus carbon dioxide gas produces aqueous urea plus water. So we have to write a balanced equation. So here's our balanced equation. 2 ammonia, carbon dioxide, urea, water. So we have products over reactants. We don't show water, it's a liquid, we ignore it. So here's our equilibrium constant expression. We're going to practice another one. So this is silver chloride solid, dissolves into silver ions and chloride ions. So here's our silver chloride, and then it's breaking up into silver ions and chloride ions. So here's our K expression. So you should be able to do that. Practice another one. Calcium carbonate solid decomposes to calcium oxide solid and carbon dioxide gas. So we've got solid, solid, gas. So our K is just going to be the partial pressure of our carbon dioxide. Our solids do not appear in the expression. Lead 2 iodide solid dissolves into lead ions and iodide ions. So here's our lead 2 iodide in equilibrium with lead ion and iodide ion. So our K expression just includes the products. Remember, we have a coefficient here, so it's the power of 2. So one more. Aqueous hydrogen ion combines with aqueous hydrogen carbonate ion to form water plus carbon dioxide gas. So here's the hydrogen ion, hydrogen carbonate ion in equilibrium with water and carbon dioxide gas. So partial pressure of the CO2. This is a liquid. It does not appear in our expression. H plus. And then the HCO3 minus. So we're going to want to use this equation. So it's this one. Okay, so we're going to use that to find our delta G in a non-standard state. We're going to use the delta G at a standard state, but we have to add RT natural log of Q. Remember, Q has the same expression as K, but it may or may not be at equilibrium. So we're going to be able to calculate the delta G in the standard state because it's this other equation. This is a different one. So this is the basic equation relating the standard state free energy change to the equilibrium constant. You absolutely must know this. Delta G of the standard state equals minus RT natural log of K, where K is the equilibrium constant. So we're going to do an example. Find the value of the equilibrium constant K for the formation of urea at 25 degrees C. We're given the delta G of formation of urea as a minus 204 kilojoules per mole. So here's our equation. 2 ammonia, carbon dioxide in equilibrium with urea and water. So these are from tables. So minus 16.6 for the ammonia, minus 394.4 for the carbon dioxide, minus 204 for the urea, minus 237.2 for the water. we have to use our coefficients. So this is going to be our products. So 1 mole minus 204 kilojoules per mole plus 1 mole minus 237.2 kilojoules per mole. Those are our products. We're going to subtract our reactants. So we've got some stoichiometry here. So 2 moles minus 16.6 kilojoules per mole. 1 mole minus 394.4 kilojoules per mole. The products minus reactants. We get a minus 13.6 kilojoules. The moles cancel. So if we rearrange this equation, we can subtract both sides by minus RT. And that's how we get natural log of K equals minus 13.6 times 10 to the 3 joules over minus 8.31 joules over Kelvin mole times T, which is 298. And then we solve for K. And so we were able to obtain K from knowing our delta G. The way that we did that was we used this equation. Okay, so this question is asking you to find the K and explain where the equilibrium lies. So these are the delta G values. Calcium carbonate minus 1128.8. Calcium oxide minus 604.2. Carbon dioxide gas minus 394.4. They're all 1 to 1 to 1. So we're going to do products minus reactants here. So go ahead and copy that down. When you do the math, you get 130.2 kilojoules. This is the equation we're going to use. Natural log of K equals delta G at standard state over minus RT. So we put our delta G on top. This is our R, that's our T. Take the analog of both sides. So we get our K. So our K is 1.47 times 10 to the minus 23. It's very small. That means the equilibrium lies towards the reactants. Now we're going to calculate the KSP for the dissociation of silver chloride. And we're going to use our delta G values. So here's our equation. Silver chloride in equilibrium with silver and chloride. We plug in our values from the table. So minus 109.7, 77.1, minus 131.2. The units are kilojoules per mole. Everything's 1. So our delta G at standard state is 1 mole. This is our products. So 1 mole times 77.1 kilojoules per mole. Plus 1 mole of minus 131.2 kilojoules per mole. So this is products. Minus our reactants. 1 mole minus 109.7 kilojoules per mole. We get our delta G is 55.6 kilojoules. We plug it into our expression. Here's our delta G over minus R, and there's our T. Take antilog of both sides, and we get our K is 1.77 times 10 to the minus 10. Our equilibrium lies towards the reactants. So let's look at delta G and temperature. We have a nice little table here. So we're going to assume that the change in enthalpy is delta H, and the change in entropy, that should be a delta S, so I have to fix that. Okay, so right here should be a delta S. Our constant. The greater the actual temperature is from 25 degrees C, the greater the, and I'll have to fix that. Text. Why is this not working? Okay, so let's just fix this. Assume that the change in enthalpy delta H and the change in entropy delta S are constant with respect to temperature. The greater the actual temperature is from 25 degrees C, the greater the error in our assumption. So let's look at some situations. So the first example, our delta H is negative, our delta S is positive, our delta G is negative. This is spontaneous at all temperatures. Our example is C6H12O6 solid going to 2C2H5OH liquid plus 2 CO2 gas. You're not going to be given an equation and asked to know this. You're going to be given these situations and have to know this column. So next, delta H is positive, delta S is negative, delta G is positive. This is non-spontaneous at all temperatures. So for example, 3O2 gas going to 2O3 gas. Next situation, delta H is negative, delta S is negative, delta G can be either positive or negative. In this situation, it's spontaneous at low temperatures and non-spontaneous at high temperatures. So for example, to ammonia plus CO2 gas going to urea plus water. Next situation, better if we can see the whole table. So this is our delta H is positive, delta S is positive, delta G is positive or negative. This is non-spontaneous at low temperatures, spontaneous at high temperatures. So for example, barium hydroxide decahydrate plus ammonium nitrate solid goes to barium nitrate solution plus ammonia plus 10 waters. To remember, if the delta S is positive, you have an increase in entropy. If you have a negative delta H, it's exothermic. So just a reminder, you will not be asked to predict the spontaneity of these individual reactions. Questions about this chart are typically multiple choice questions giving the sign of delta S, delta H, and delta G, and you're asked about the effect. Okay, we're going to do an example. What's the delta G at 1000 degrees Celsius for the following reaction? Is this reaction spontaneous at 1000 degrees C? And 1 atmosphere, what is the Kp at 1000 degrees C? What is the partial pressure of CO2? Okay, so let's just start by calculating the enthalpy. So we're going to plug in the enthalpy values from our chart, our table. So minus 1206.9, that's for our calcium carbonate. Minus 635.6, that's for our calcium oxide. Minus 393.5, that's for our carbon dioxide. Units are kilojoules per mole. Let's just simplify everything because everything's 1 mole. So these are products minus our reactants. So minus 63.6 minus 393.5, subtract our reactants, minus 1206.9. So we get a we get enthalpy of 178.3 kilojoules. So this is our enthalpy. We're going to do the same thing, but now we're going to calculate the entropy. We get the entropy values from the table. So calcium carbonate, 92.9. In equilibrium with calcium oxide, 39.8. Plus carbon dioxide gas, 213.6. And the units are joules over mole Kelvin. Again, these are all 1 mole, so let's just simplify. So products minus reactants. So 39.8 plus 213.6. Subtracting our 92.9. So for our entropy, we get 160.5 joules over Kelvin. Now we're going to plug everything into our delta G equals delta H minus T delta S. We calculated our enthalpy up here, so we plug it in here. Our temperature, we converted to Kelvin. Our entropy, we're going to change the units to kilojoules. So here was our entropy in joules per Kelvin. We changed it to kilojoules per Kelvin. Now we just do the math. We get that the delta G is a minus 26 kilojoules at 1000 degrees C. So then we plug this into our expression of natural log K. Looks like I forgot to do the K there. Let's fix that. I thought they were perfect this time. So natural log of K equals our delta G over minus RT. So here's our delta G. Plug it in here. My little pencil guy. Oh, my hand guy's good. Okay, so here's our delta G. Plug it in here. It was a negative. We still keep it as a negative. Notice that we changed from kilojoules to joules. Here's our minus R, and here's our T. So when we do that, we get our K by taking antilog of both sides. We get 11.68. So let me subtract my little guy here. There's my little eraser. Okay, the next part of the question asks for our KP. So this is K, it's our KP, same thing. We're just labeling it as KP. And then because of our expression for KP, our KP equals our concentration of CO2. And so our concentration of CO2, or actually pressure, is 11.68 atmospheres. And there you have it.